Hello, psychology students. This is Mrs. Politsky, and I have your notes for Module 8, Sensation, and we're going to talk about hearing. So, there has always been kind of this debate about if a tree falls in the forest, and there's no one there, is there a sound? And psychologists, and it probably should say psychologists, believe that there are sound waves, but there is no sound or noise because sounds and noises are basically a psychological experience created by the brain in response to stimulation. In other words, to actually hear something, something has to be present at the time to receive that audio experience. So, the nature of sound. Sound waves are produced by vibration, and you can feel your vocal cords vibrate if you touch your neck while you're singing or talking. When we talk about musical instruments, they all produce some kind of vibration. Strings, for the case, on guitars or violins or pianos. Reeds, when we talk about saxophones or clarinets. Drums, when you talk about like the skins or the drum heads, like on a timpani or bass drum. Typically, the vibrations travel in pulses of air molecules. But other substances can carry sound waves too, such as the bones that are in our skull, transmitting sounds of a fast beating heart to our ears, or maybe even water in a swimming pool, transmitting sounds of music to swimmers or to the ears of maybe synchronized swimmers. The frequency is the number of cycles per second in a sound wave. So it's the primary determinant for what we call pitch. And for sound, the length of the wave or the frequency determines that pitch. So it all depends. So to kind of put things in perspective, I'm going to have you grab your diagram sheets. And what we're going to do is we're going to label this diagram that you guys received a few days ago. We're going to start with the outer ear. Okay, and then moving inward, we have our auditory canal. And at the end of the auditory canal is a thin piece of tissue. This is the eardrum or tympanic membrane. Beyond that are a series of three bones: the hammer, the anvil, and the stirrup. And if you take a look there on our diagram, the stirrup really does look like a stirrup, maybe on a saddle of a horse. We have a series of like tube-like structures that kind of come near, and that is our oval window, and it kind of leads to the ossicles. And then that cone shape that you see there that maybe looks like a snail, that is our cochlea. And then finally, we have our auditory nerve. So you can kind of see it a little bit better maybe from the diagram in your book. But as sound waves travel in, they are going to literally hit that tympanic membrane or the eardrum, and it's going to cause that to vibrate. And as a result, the bones of the middle ear are going to start moving, and eventually it's going to stimulate the cochlea. And inside of the cochlea, we're going to have our sensory receptor cells, sometimes known as hair cells or the basilar membrane, which are going to be stimulated. And that energy is going to be traveling down through the auditory nerve to the auditory cortex that's in the temporal lobe. So, going back to talking about sound, pitch is the highness or lowness of the tone, which determines the frequency of the sound wave. And so you can kind of see, um, maybe from the waves that we have here, this kind of works not only for hearing, but it also works for color to a certain degree. But if you take a look at the short wavelengths, the shorter the wavelengths, or you get a higher frequency and you get a higher pitch sound. The lower the wavelengths, the lower the frequency, the lower the pitch the sound. So pitch is always expressed in hertz, or the HCs. It's a unit of measurements for frequencies, or the number of sound waves that reach the ear per second. Your amplitude is the magnitude of the wave. In sound, that's a primary determinant for loudness. And the height or the amplitude of that sound wave determines that loudness, and it's also measured in what we call decibels. Decibels, at least the B part of it, was named after Alexander Graham Bell. Any prolonged noise, including music, will gradually produce irreversible hearing loss. So, some examples of really high to low decibels. If you were standing right next to a revolver or a gun at a close range, you're probably getting over 130 decibels, probably requiring some kind of ear protection. Same goes with sonic booms, an air raid siren, or like an emergency management siren, fire siren, if you want to call it that. Jackhammers at roughly 3 feet. I mean, it's extremely loud. If you're near an airport, a jet plane at roughly 500 feet above you, going full tilt, that's going to be loud. Personal stereos at full volume. If you go to a concert, a very loud concert, easily 100 decibels. Getting below that, you might have a subway train at roughly 20 feet, jackhammer at 20 feet, heavy truck at about 25 feet, lawnmowers, food blenders. All of these things can cause potential ear damage. Even things like sewing machines, as crazy as that may seem, can possibly cause that irreversible hearing loss. 80 to 60 decibels, heavy traffic, vacuum cleaners, dishwashers, well, the old fashioned ones, not so much the new ones, but normal conversation. 60 to 40, you're going to have some air conditioners, patterns of rain, if it's a heavy rainstorm. 40 decibels is kind of like the normal sound of an office interior or maybe even a schoolroom. And then finally, at about 20 decibels, the rustling of leaves and a whisper at only a few feet. So, the structures of the auditory system, when we talk about the traveling of the sound waves, the vibration that constitutes the sounds must travel through the air to our ear. And when the sound wave reaches the ear, it will travel down the auditory canal, basically an opening through which sound can travel. It kind of gets funneled into for basically processing. At the end of the auditory canal, the sound waves reach that piece of tissue that seals the inner workings of the ear called the eardrum or the tympanic membrane. Just going just here for a second, the tympanic membrane, if there is a loud, extremely loud noise, it's possible that membrane can be broken, and you would have damage to that, making it kind of hard to hear for a period of time until that healed. Anyone who has had like tubes in their ears, a lot of times that's where they put the tube. They put it there on the tissue to relieve pressure of the inner ear. So let's keep going here. The eardrum transmits vibrations from the air to basically three tiny bones, which we talked about. These bones are called the hammer, the anvil, and the stirrup. So the hammer hits the anvil, and hopefully the blacksmith will make a stirrup out of it. That's how I remember it. Anyway, because they are vaguely resembling these objects, that's why they get the names. Attached to the back of the eardrum are also the ossicles. These are the tiny mechanisms that consist of these three bones. Sound waves are transferred at that point to the cochlea, and it's a fluid-filled, snail-shaped, bony tube in the inner ear where sounds are really changed into those neural impulses. This is where we're going to have the receptor cells for the most part. And the point on the surface of the cochlea that receives the vibrations from the ossicles is basically, we should probably have something there, is the cochlea. Inside the cochlea, vibrating fluid stimulates thousands of what we call hair cells. And those hair cells are the receptor cells for hearing and are responsible for changing sound and vibrations into those neural impulses. From the receptor cells, the neural impulses travel via the auditory nerve. This is the nerve that carries the sound information from the ears to it should be the auditory cortex, since this is not going to move on me, where the auditory processes occur. Okay, sound localization. Mammals are really good at localizing sound. It provides them important environmental information about where danger is and such. And sometimes we use it when we're trying to figure out where things are located. So, like, if I'm trying to, um, if I'm walking down the hallway, I'm trying to figure out, um, where the doorway is. If I cannot see it, I can use the localization to kind of hear the differences of that. So, the how this works is step one is to determine which ear hears first. So, are you hearing with your left or your right, or are you hearing with both ears at the same time? Sound travels very quickly at roughly 750 miles per hour. The second step is determining which ear hears louder, the more intense sound. Sound perception, we get monaural cues. These are the cues for sound location that requires only one ear alone. Um, Changes in loudness can be perceived by changes in distance. And then we have like the aural cues. This is sound location that's using both ears working. Stereos kind of work on this, but if you ever watch like a dog, they have a tendency to move their ears if they're listening for something at the same time. And what they're doing is they're using this aural cue to kind of figure out where things are in their environment. Thank you very much.